In this lecture, I'm going to discuss how you can solve an n-order linear homogeneous equation with constant coefficients. So the only difference with a regular n-order linear homogeneous equation is that now all coefficients a0 through an are constant. Now, mainly I'm going to describe everything in terms of second-order linear homogeneous ODEs, so something like this. And then briefly at the end, we're going to talk about higher order equations because the methodology for solution is going to be exactly the same. So learning about second order equations would be enough. We're trying to solve an equation like the one that I circled here. A particular example of second order linear homogeneous ODE with constant coefficients is an equation like this, but not an equation like that. Both are linear equations, second order, but the circled equation has some of the coefficients depending on x, while what we're talking about now are equations with constant coefficients. All right, so let's suppose that we have this generic second order equation and I want to solve it. So let's write this down. Want to solve a2y double prime plus a1y prime plus a0y equal to 0. Somehow we can try to guess the form of a solution of this equation. Guess it on the following, based on the following considerations. So what we're doing here, we're adding first and second derivative of y to y itself with constant coefficients, and at the end of the day, we're getting 0. So that means that the first and second derivatives should resemble the function y. The form should be similar to the form of the function y. And if you think about what type of functions will have this property that their derivatives are similar to the function itself, then an immediate example that comes to mind is an exponential function. And so what we're going to try to do is we're going to try to find the solution in the form of an exponential function. So we're going to try a solution in the form y equal to e to the power rx, where r is a constant. At this point, it's an unknown constant. Okay? So if we think that a y like this is going to be a solution, then if I plug it into the equation, then the equation must be satisfied. So if I have y like that, then y prime is r e to the rx, and y double prime is going to be r squared e to the rx. Then I will substitute this into the equation. And once I substitute this solution into the equation, then I'm going to get a2 r squared e to the rx, right, for a2 times the second derivative, plus a1 times the first derivative, which is written here, and plus a0 times the function, which is e to the rx. And I want that to be equal to 0. All right, so then if I look at this new equation that I got, then I see that on the left-hand side I have e to the rx as a common factor, so I can factor it out. And inside I'll have left a2r squared plus a1r plus a0. The whole thing is equal to 0. All right, so then exponential function is never 0. So because e to the rx is not equal 0, I can divide this by e to the rx, and once I divide both sides by e to the rx, I'm going to get a2r squared plus a1r plus a0 equal to 0. So what I get is a quadratic equation for r, and there are no x left here, right? So I just have a quadratic equation. This is not an ODE, so I should be able to solve it as a quadratic equation. This guy in the future is going to be referred to as a characteristic equation for our ODE. All right, and so because it is a quadratic equation, remember that a1, a2, and a0, those are all constants. So how do I solve a quadratic equation? Of course, I can use a quadratic formula. Which I'm sure you all remember. And once I solve it, I get that r is equal to minus a1 plus or minus square root of a1 squared minus 4 a0 a2 to the power 1/2, everything divided by 2a2. Okay, so this is our characteristic equation. This is its solution. And as usual, right, for a solution of a quadratic equation, we have three different possibilities. So we have three choices. Choice number 1, a1 squared minus 4 a0 a2 is greater than 0. In this case, I can take this square root. And once I take a square root, then I get two solutions. So I have two solutions. R1 and R2. Of my characteristic equation. And so out of these two solutions, I can get, right, If R1 and R2 solve the characteristic quadratic equation, then it means that e to the power Rx solves the original ODE, right? And so that means that I got two different functions, e to the y1 equal to e to the r1x, and y2 equal to e to the power r2x. They both solve my ODE. And further, or clearly, e to the power r1x is not equal to constant times e to the r2 times x, right? Because I have two different solutions, r1 and r2, they're not the same. So exponential to one power is not a constant times exponential to a different power. And therefore, y1 and y2 are going to be linearly independent. And if they're linearly independent, that means that I have a second order equation, and I got two linearly independent solutions of this equation, so then what I got is a fundamental set of solutions, and therefore the general solution of my ODE is going to be a linear combination of these two solutions. So it is y of x equal to c1 y1 of x plus c2 y2 of x. y1 is e to the r1x plus c2 y2 is e to the r2x. So the moral of the story is that in this first case, when the expression under the square root is positive, I get two different solutions of the characteristic equation, and as a result I get two linearly independent solutions of the ODE, and if I combine them in a linear combination, then I get a general solution of my ODE. Let's do choice number 2. The second choice is going to be that the expression under the square root is no longer positive, but it's equal to 0. So a1 squared minus 4a1 a0 a2, this is equal to 0. All right, so what do we have in this case? Then r is going to be equal to minus a1, right? So if the square root is equal to 0, then you have only one solution, right? Because minus a1 plus minus 0 is just minus a1. So minus a1 over 2a2 is the only solution of the characteristic equation. And then if that is a solution of the characteristic equation, then e to the power this r times x is going to be the solution of the ODE. So then e to the rx is a solution of the ODE. But I'm trying to find the fundamental set of solutions, so I need not just one solution, but two. So how do I find the second solution? That is the stuff that we learned in the previous section. how do I construct second solution from the first solution? I will just use the method of reduction of order. So use the method of reduction of order to find the second solution. Okay, so how do we do that? First, we need to write the equation in a normal form. Write the ODE. In a normal form. For that, we go back to the ODE. It looks like this. So in the normal form, we need to divide by A2. So once we divide by 2, the equation becomes y double prime plus A1 over A2 y prime plus A0 over A2 y equal to 0. Okay, so then we use the method of reduction of order formula. So then y2 is equal to, let's remember the method of reduction of order. The formula is y1 integral e to the minus integral of p of x dx divided by y1 of x quantity squared dx. Now, who is y1? y1 is e to the rx. Then we have an integral. Again, y1 is e to the rx, so e to the rx quantity squared in the denominator. And then e to the power minus integral, what is p of x? P of x is a1 over a2, that's a constant. So a1 over a2 dx. Fine. And now, one other thing that we know is that r is minus a1 over 2a2, so I'm going to substitute that choice of r into my formula here. So, and I'm going to keep e to the rx the way it is outside, so I'm only going to make a substitution inside the integral. What is integral of a1 over a2? That's minus a1 over a2 times x. And e to the rx is e to the minus a1 over 2 a2 x squared dx. But then if I take a square of the exponential, so e to the power something times x squared, I have to multiply the powers, and that will give me, so minus a1 over a2 x on the bottom, and a1 over 2a2 twice is again a1 over a2. So e to the minus a1 over a2x again dx. But then the stuff on the top is the same as the stuff on the bottom, they cancel. Then integral of dx is just x. So what I got is x e to the rx. And I know that the second solution is linearly independent from the first one because that counts as a reduction of order. The second solution that you find from a reduction of order is always going to be linearly independent from the first one. And so therefore, y1 equal to e to the rx, y2 equal to x e to the rx is a fundamental solution, fundamental set of solutions of my ODE. And hence a general solution in this case is y equal to c1 e to the rx plus c2x e to the rx. All right, so that means that we have been able to find the general solution of our ODE, both in a case when you have one solution and in a case when you have two solutions of the characteristic equation. And now we're left with the third case. So case number 3. And that is when a1 squared minus 4 a0 a2, when this quantity is less than 0. Okay, let's see what happens in this case. So before we go any further, let's go a little bit further first. So therefore, in this case, right, remember, our two solutions, R1 and R2, are equal to minus A1 plus or minus square root of A1 squared minus 4A0 A2 to the power 1/2 divided by 2A2 in the denominator. Now, in this case, clearly R doesn't have any real solutions. The quadratic equation, characteristic equation, doesn't have any real solutions because the expression under the square root is negative. But you might recall from most of you probably should have seen complex numbers before. Complex numbers allow you to take roots of negatives. And in particular, I can take a root of a negative here in the following way. So this is minus a1 plus or minus. I'm going to factor out minus sign inside the square root. So that I'll have minus 4a0 a2 minus a1 squared to the power 1/2. So if this quantity is less than 0, then minus of that quantity is positive, right? It's greater than 0. And divided by 2a2. And the square root I can always distribute then between, if I have a product inside the square root, I can distribute the square root between the terms of the product. So this is minus a1, then square root of minus 1, and then square root of 4a0 a2 minus a1 squared. And I'll write square root as 1/2 power times 2a2. And I'm missing plus or minus, so let me add it here. Plus minus. And so finally, for complex numbers, right, square root of minus 1 makes sense, and it's an imaginary number I. So what you get is minus a1 plus or minus I for a0 a2 minus a1 squared to the power 1/2 divided by 2a2. And finally, I can split this into a sum of two things. Minus a1 over 2a2 plus or minus. I'm going to write the real number that I have here, 4a0 a2 minus a1 squared to the 1/2 divided by 2a2. And this has to be multiplied by this imaginary number I. And I'm going to introduce the following notation. I'm going to call this number alpha, this number without plus or minus beta. And so what I got is that my solution of the characteristic equation now looks like alpha plus or minus I beta. Right, so if I know A1, A0, and A2, then I know exactly what alpha and beta are going to be. And so that means that I know these numbers. We're going to call this complex conjugate numbers. When you have alpha plus I beta and alpha minus I beta, those two are called complex conjugate. And so therefore, in principle, when you talk about complex numbers, you work with them in the same way as you do with real numbers, except that now you're allowing for square roots of negatives. And so in this case, I should still be able to write the solution of the ODE. So solution, in fact, we can write the general solution. Complex. Solution of the ODE is going to be a linear combination of e to the, remember, that's what we have done. We found two possible choices of r, right? There are two complex conjugate numbers. If r solves the characteristic equation, then e to the rx solves the original ODE. So I have two solutions, e to the power alpha minus I beta x. I have a second solution, e to the alpha plus I beta x. And my general solution is going to be C1 times the first solution plus C2 times the second solution. And in this case, they're still linearly independent. So this solves the ODE. But now C1 and C2, because my solutions are complex, again, you might not have dealt with complex numbers a lot, or if at all, but if I can solve the ODE, if I have two solutions of the ODE that are complex, then in principle C1 and C2 that I choose also have to be complex. So where C1 and C2 are arbitrary complex numbers. Okay, so I found the general solution of my ODE, but unfortunately the general solution is complex. And certainly I would like to have a real solution, because we're solving an equation, an ODE, which does not have any complex numbers in it. Okay, so what can we say about this? Let's play the following game. So I'm going to take the solution that I found, and I'm going to try to simplify it a little bit or write it in a slightly different way. So let's put it here. As with any exponential, actually this is a fact that many of you missed on the test, with any exponential of a plus b, so if I have a plus b in the power, then e to the power a plus b is going to be e to the a times e to the b, not e to the a plus e to the b. So I'm going to take advantage of this fact here. This is c1 e to the, I'm going to distribute x, alpha x minus I beta x plus c2 e to the alpha x plus I beta x. I'm going to write this as c1 e to the alpha x minus I beta x. I can write again as a product of two exponentials, e to the alpha x times e to the minus I beta x, and I can do the same thing for C2. Here it is e to the alpha x, e to the I beta x. And then there's a common factor of e to the alpha x, which I can pull out. And inside I have C1 e to the minus I beta x plus C2 e to the I beta x. If I look at e to the alpha x, this is already a real number, because alpha is a real number, x is a real number, e to the alpha x is a real number. So the only complex stuff is inside the parentheses here. Okay, so I just said that my ODE can be solved by this complex solution here for any choice of C1 and C2. So what I'm going to do, I'm going to choose C1 and C2 both equal to 1/2. In this case, then what am I going to get? I'm going to get e to the alpha x times 1/2 e to the minus I beta x plus 1/2 e to the I beta x. And that I can also write as e to the alpha x times e to the I beta x plus e to the minus I beta x divided by 2. Here you have to know the following formula. If I have e to the power I theta, then I can write e to the I theta. This is something that when you study complex numbers, this is a formula that you arrive at pretty quickly. It looks funny, but it is true. So e to the I theta, this is so-called Euler formula. E to the I theta is equal to cosine theta plus I times sine theta. So in terms of complex numbers, it turns out that exponentials and trig are related. Okay, so if this is true, then I should always be able to write the thing that I just written here in the following way. So it's e to the alpha x. I look at e to the I beta x, right? That's like e to the I theta, with theta being equal to beta x. So e to the I beta x is cosine of beta x plus I sine beta x. That is for e to the I beta x. But e to the I minus I beta x can be written down in a similar way, except that theta now is minus beta x. So plus cosine minus beta x plus I sine minus beta x, and the whole thing has to be divided by 2. Right, so I have my Euler formula. I simply use this here on my complex numbers, and I'm going to get the stuff that I have written in the last line here. So let's continue. E to the alpha x cosine beta x plus I sine beta x plus one result that you should remember is that cosine is an even function. Cosine of minus something is equal to cosine of plus of the same thing. So cosine of minus beta x is the same thing as cosine of beta x, because cosine is an even function. Likewise, sine is an odd function. So sine of minus beta x is minus sine of beta x, still divided by 2. And now what do I see? I see I sine beta x and minus I sine beta x go away. And what is left is cosine beta x plus cosine beta x, that's twice cosine beta x divided by 2. Only one cosine beta x remains, and so e to the alpha x cosine beta x is a solution of my original ODE, because the original ODE is solved by this complex function no matter what C1 and C2 are. So if I have C1 and C2 equal to 1/2, then actually instead of complex function I end up with a real function, because the complex part is equal to 0. So this then is a real solution of the ODE. Okay, and so then that's one real solution. Then of course I can find the second real solution in a couple of different ways. I can find the second solution by using the method of reduction of order, or I can use it I can find it in a similar way, as follows. Now I'm going to choose C1 and C2 in the following way. So choose C1 equal to minus 1 over 2i, and C2 equal to 1 over 2i. So if I do that, then I end up, let me just copy this stuff from here, and we'll modify it accordingly. So then, what will happen? So C1 is minus 1 over 2i, so this is minus 1 over 2i, and C2 is 1 over 2i, so just like that. So then if I factor out 1 over 2i, then inside I'm going to have left e to the I beta x, because it comes with a plus sign, minus e to the minus I beta x, it comes with a minus sign. Fine. So 2i on the bottom. The only difference with what I had before on the top is that plus became minus. So that means that this is minus, and so is this. All right. So cosine of beta x is still the same thing. Sine of beta x is still the same thing, because this didn't change. Cosine of minus beta x is cosine beta x, but now there is a minus sign in front. And for this guy, it is plus sign instead of minus sign. And there is 2i on the bottom. So now cosine cancels out, and what I will have left is e to the alpha x, and on the top 2i sine x divided by 2i. 2i cancels out, and what is left is not sine x, but sine of beta x, sorry. So e to the alpha x times sine of beta x is a second solution, and this is also a real solution of the ODE. And so after all of this hard work, what we get two real solutions of ODE. One is here and one is here. And clearly one is not a constant multiple solution of another, because one has cosine, another has sine. Cosine is not a constant multiple of cosine. And so therefore, general solution, general real solution of the ODE is going to be y of x equal to c1 e to the alpha x cosine beta x plus c2 e to the alpha x sine beta x. And of course we can factor out e to the alpha x, so y of x is e to the alpha x c1 cosine beta x plus c2 sine beta x. And so this hard work allows us to do what? It allows us to solve the ODE, this second order linear homogeneous ODE with constant coefficients. It gives us the form of a solution for each of these cases, right? Either it was, in case 1, it was a combination of two exponentials. In case 2, it was a combination of an exponential and x times the same exponential. And in the third case, we get exponential times a combination of two trigs. And in the next lecture, we're going to discuss particular examples of how you apply these formulas. All right.